Right, so energy balance, by the way, you'll find this in the Dropbox folder. So I just uploaded it. So you can get this PDF from there. So in this energy balance, as we said, in the isothermal case, we've got the temperature being the same at all points across this reactor. And if we think about most reactions, that's simply not the case. Right, you have some collection of reactants, and even in the simplest possible case, even if it's just A going to B, then the energy state between those two is generally different. So the molar enthalpy of A is different to the molar enthalpy of B. And what that means is our molecules are in a different energetic state. So there might be the same temperature, they will be at the same temperature, for example, in the CSTR case. But for A to translate to B, some energy is required to break bonds and remake bonds. And the way that B looks, the way B is structured, may require more energy than, for example, A. So there is a difference in the energy configuration of these two types of molecule. And so even in the simplest possible case, we still expect there's going to be some energy needed for this reaction to occur and for these molecules to be stable. And so what will tend to happen is the energy is taken from the surroundings or added to the surroundings by the reaction. And so we don't expect that during the reaction, the energy, the thermal energy, let's call it the thermal energy, we don't expect that that's going to be the same. The temperature is going to change in that reactor. I saw an unmute just now. Did anyone have a question or a comment? Okay, so we've got our species that are reacting, and we expect that there is going to be a change in the temperature in the reactor. So we need to then consider doing an energy balance as a way to keep track of it all, right? And we also anticipate that this is important to do because the temperature, right? So when we talk about the energy changing in the system, we automatically think about temperature, right? So more energy in the system might mean that the temperature will also change quite a lot. And like we said, I think it was in the very first lecture, that it is often the case that the reaction rate will double for every 10-degree rise in the temperature. And obviously that's just a rule of thumb, and it's not generally true, but quite often the change of reaction rate is on that order, right? The reaction changes on the order of 2 times per every 10-degree rise. And so that's why we are so sensitive to any temperature changes. That's why reactors often look like heat exchangers. You'll see cooling jackets or heating coils that are installed on these reactors, and that's all to try and control the temperature in that reactor. So we want to now, in the face of energy changes across that reactor, in the face of temperature changes, still be able to do the things we were doing on the Levenspiel plot and estimate how big must the reactor be, what's the actual reaction rate in the reactor. And we have to acknowledge at this stage, we don't even know what the reaction rate is going to be anymore. Right before, we could just say Ra equals K times Ca. So even in this simple first order reaction, we were often given some kinetic rate constant, and we did some calculations. This was often written in terms of the conversion, and that's how we worked. But this K is most often a strong function of temperature. And of course, we have the Arrhenius relationship. So we know using an Arrhenius relationship, well, the standard form to write that equation is, of course, like this. So the kinetic rate constant as a function of temperature is the pre-exponential factor times the exponential of minus E, the activation energy, over RT. So that's the standard form of the Arrhenius relationship. But if you were to work out, if you were to use the same expression at some specific temperature, right? So let's say this was at this temperature T1, and let's say we called this K1. Then if you take K at some T divided by K1, and then divide on this side, the A's will cancel, and you'll end up with K of T over K1 equals, so the A's cancel, and when you divide exponentials, then you can simply add the exponential factors. And so this is going to end up being minus E over RT, and so here it's going to be 1 over T minus 1 over T1. So we can write the Arrhenius expression, or we can write it in terms of the reference, in terms of some reference number. So if you like, this is a way to correct our kinetic rate constant for a temperature that's different to a reference temperature, right? So we know E is typically a big number. It's on the order of tens of thousands. And that's how we end up with such a reaction on the, or such a response on the kinetic rate constant. So K itself changes quite quickly with the temperature. Then also there are some reactions, well, gas phase reactions. We know that the concentration does change with temperature as well. So if you have a gas phase, even if the pressure is low enough to use the ideal gas law, still you can see that the concentration is a function of temperature. And so your concentration also does change with temperature. So for two separate reasons, your reaction rate is going to change with temperature. And of course, our balance is then dependent on T and the reaction rate. So we need to revise our balance. And now, of course, when we started our development, when we did the mass balance, we wrote an equation like this: dNA dt equals, and we took the molar flow in, and we subtracted the molar flow out, and we added the change due to reaction. So this was the integral of A in V, right? So that was what we wrote. Now, to develop our energy balance, we are going to take a similar approach. And now, instead of counting moles, right, that whole balance we developed from looking at a picture like this. And we talked about packets of moles entering here. So we can think about packets of energy entering. So how would we start to develop a balance? Of course, we have the concept of enthalpy. Let's for now just say EI is the energy per mole of component I. And so our tendency would be to say, then the rate of change of energy, ddt of the energy, so the energy is going to look something like NI times EI. And then we would want to write something like we have here, right? So we would say, then the rate of change of the energy is going to be the energy coming in. So EI in, and then EI out, so the energy coming in and the energy going out. And then we would also say, well, then there's the reaction that's happening, and so well, if I'm writing this in I, so then we would say E sub I like that. Does this look reasonable? Does anyone agree or disagree with the way we've written this energy balance here? Maybe just thumbs up if you agree with this balance. And okay.
Sorry.
Yeah.
So may I ask if do we need to include the energy generation or in this equation?
Yeah. So in effect, what we are saying is this is the energy generation due to the reaction. Is that what you are asking there?
Yes.
Okay, so let's keep going with that. So do you agree then that this equation makes sense?
Yes.
Well, let's think about that. We are saying we are generating energy here. And can energy be generated? Can we create or destroy energy? And I think
no.
Thanks. So yeah, you can't generate energy. So even though the reaction is happening, it's not the case that it's just going to give us energy spontaneously, right? And I mean, it's a little bit of a trick question because there are, of course, different forms of energy. You've got thermal energy, right? The energy that you experience in the form of temperature changes. Then you've got a kind of chemical potential energy. So energy that's locked away in terms of the atomic structure, the way the bonds are arranged and the amount of energy it took to make and break bonds. But if we are intending by this to mean the total energy, and we should have put little summation signs over I to add up over all components, in terms of saying that we are generating energy by the reaction, we can't say that. The only truth is that the total amount of energy must be the same. So we would actually remove that and we would say the total energy, and let's do it. Let's add the little summation signs here. So, so the sum in each case this is all we can say, right? So we can say that the sum of the energy contributions from each of the species, this should be an I here also, and that should be an I comma. So we can say the total energy in minus the total energy out is going to be the total rate of change of energy in that reactor. So this strictly follows the conservation of energy law. And the funny thing is, there's no reaction here, and yet we know that there is a concept like heat of reaction. So it, on the one hand, yes, this respects the conservation of energy. On the other hand, where is the heat of reaction? Why do we not have that? We know such a thing exists. And by the way, just a note that when we write the mole balance, of course, the moles are not conservative. So you have conservative properties, energy, mass. We consider those conservative properties of nature. Number of moles is not conservative. In the same reaction, you can have more moles appearing than you had in the first place. There's nothing wrong with that, right? You can have a situation like this. So your mass can stay the same, but your moles could be increasing or decreasing or whatever. So that's why in the mole balance, it's pretty automatic to add that in, but we can't have that in our energy balance. Okay, so that's just a principle for us to bear in mind. And let's see what we can do with that. Right. So here under misconception, yeah, that's what that's the misconception, right? Of course, that's true. And here I'm also making the point in terms of the total mass. So this is number of moles we know is changing. We also know the total mass is also conservative. Mass is also conservative. So the total rate of change of mass is the inlet minus the outlet. And then if we add this term in here for the reaction, we'll find that this is 0. In fact, in one of the previous sessions, we made this point that if you were to multiply the molar mass, we actually use the fact that this equals 0 to work out a molar mass. So there was a problem where we didn't know one of the molar masses, and we used the fact that this must equal 0 to get that molar mass. So so this also applies in terms of mass. Okay. Any questions or comments there so far? Okay, now we would like to develop this energy balance. So let's think about all the possible forms of energy contribution to the system. Of course, we have our first law of thermodynamics, that the total energy change is equal to the thermal energy change and the work energy change. So when we say thermal energy change, whenever we write a delta Q in this course, we mean energy added to or removed from the system as a result of temperature differences. So if we apply, for example, let's say we have the CSTR, and let's say we have this heating jacket here, then this temperature in this jacket is higher than the temperature in the reactor. So there'll be thermal energy added from the jacket into the reactor. Or if this is a cooling coil, then that coil is absorbing energy from the reactor into the coil, and it leaves through what's flowing in the coil. So temperature difference energy changes are we use the symbol the delta Q, and then we use delta W, of course, for work done on the system. So for example, if you stick a stirrer in your reactor, then this is not really changing the temperature of anything, but it is throwing fluid around. There is a little motor here, and that motor is imparting a certain amount of power, a certain amount of energy into the fluid. So that is a source of energy being added to the system, right? So our overall energy change is the sum of those two. And it's just because the conventions are different. Work is, I think the default is it's work done by the system. So that's energy that leaves the system. Whereas the convention for Q is energy added to the system by temperature difference, right? So that's why the minus sign. This actually means the sum of those two. So that's our first law of thermodynamics. We can also imagine other versions of energy. So for example, if our inlet stream is at a certain point and our exit stream is at a higher point, then there's an elevation difference, and there's a kind of gravity-driven energy influence. And so that we normally count as part of the work, part of the system. So in terms of a reactor, we normally think like this. So we've got some shaft work. So we, instead of working with such a general delta W, we say specifically the shaft work, so the work added to the fluid through the shaft that's connected to some motor, that's some contribution to energy. And then we have to look at all the heating and cooling that we do to that system. And we do that to try and maintain some temperature. Obviously, we want to maintain some reaction rate. So that's a Q. So Q dot here, that's some heat added or removed. And then we can't discount that our inlet stream here is carrying energy as well. So each of the species in our inlet stream Those have enthalpies, and so the enthalpy times the molar flow rate, that's an estimate of the energy contribution from the inlet stream. And by the same token, we have an exit stream, and we've got a certain temperature and a certain enthalpy in each of our species, and so that's an energetic loss from the system as well. So those are the kinds of influences we are concerned with. Any questions or comments there so far? Right, so our balance must look like this. There's a certain rate at which energy is changing in our system, and that's a result of heat flow from the surroundings and work done, and then the flow of our streams and the species. And so if we were to write the overall balance, it looks like this, right? So the net rate of change of energy, of total energy, equals the temperature difference energy added, and then the work done on the system added, and then the energy flow in through the stream and the energy flow out from the reactor. Note that these terms, we do have to add them. These are not, it's not like we are saying, oh, due to the reaction, we are getting this. This is not due to anything of our streams. This is, we are deliberately adding heat in the form of a coil or something like that. This is work from the shaft. So these are definitely separate forms of additional forms of energy that we have to account for. Okay. And then I guess this is a note on the units. So standard SI units, the unit of energy is joules. And then these energies, this is like energy per mole of component I. So this is a molar energy of component I. That's joules per mole. Okay, and then of course this is joules per mole, and this is moles per second. So joules per mole times moles per second, it's giving us joules per second. So joules per second is of course watts or power. Anyway, that's just the units. And then what we can do is expand on the work term. So we haven't as yet said W dot is just shaft work, right? If we look at W dot, and if that's work done, what did we say, by the system, right? W is work done by the system. So the way that the system can do work is, for example, if it's pressure and volume change. So the work done by the system by virtue of flow looks like this. So if you like, this is the momentum that your stream into the reactor is contributing. So let's see, how do we see that? So you can see this is related to the mass flow rate, and then with the pressure and the volume, that's basically momentum. So this is the momentum contribution to the reactor, and that's the momentum loss from the reactor. And then we want work done by the system, so it's a minus what you expect. And then we said, of course, the system could be doing work on the surroundings. We could view it that way also. So, so this is momentum. So we have accounted for the enthalpy change here. So just the flow in and flow out, that there's energy, chemical energy, if you like, in our species here. But there's also momentum, just the fact that the species are in flow. There's momentum work also we have to account for. So that's our work done by the system. And so we can expand in our expression. Yeah, maybe we should do this here. So is this similar enough? So that's So this is just chemical energy, if you like, and then we need to add also the work. That's the work done, and that's the heat transferred. Sorry, 1 second. I always get this interaction. Okay, so that's work. I guess that should be a minus. So that's work done by the system, and that's energy added. So that's what we have. And now we've expanded on W. So we've said W dot is the, so we've, okay, I'm just going to copy this. So W dot we've said is equal to this stuff. So there's a momentum part, and there's a shaft work part. Just bear with me. So now we've got the momentum and the shaft work in it as well. And so if we think about this expression, we can, if we expand this out, you can see there are parts of this that are not dependent on the molar amount. So for example, if you add together all the molar volumes, then you can claim that this adds up to the volume. So this is a PV. So if you extract a PV out from here, then you can write this equation by grouping those terms out. So this W dot, we'll write the shaft work here. So shaft work. So now, let's see, I don't want to lose that. Okay, let's keep that there. So that's how it looks there. And then now we need to add here. Well, I see I didn't separate them. I didn't make the assumption that you can add them. So we can just add it here. So we can say plus P dot V I in, and similar thing here. So our exit flow, we now have to say here out plus PVI out, right? So that's what we have. And now what does this look like to you? Does this type of sum look familiar in some way? Right, your favorite course, thermodynamics, what does it tell you this is equal to?
The enthalpy.
Thank you. Right, so we can rewrite this as the enthalpy. And now the equation starts to look a bit friendlier to us. HI in. Right, and I say it looks a bit friendlier because when we were writing it over here, you know, this E was quite mysterious to us. We didn't know how to count energy. This was the kind of internal energy. And of course, we should have used the symbol U here. And then we know that U plus PV, that's your enthalpy. And we know we can get enthalpy anytime. Enthalpy for any component is well tabulated. So your enthalpy for component I at some temperature T is, or let's say some, let's say over some temperature difference. Well, okay, let's just take a small temperature difference. So we'll take a heat capacity CPI, and CPI I, and then you would normally say T minus T ref, right? So if you've got your heat capacity at some reference temperature, and you want to know the enthalpy at temperature T, then you add it like that. And then, of course, you have to add the heat of formation. So the enthalpy at some reference point plus that's going to be how you estimate the enthalpy at your temperature T. And of course, all these are tabulated. You can get heat capacities for each of your species, and you typically have a reference temperature for your enthalpy. You have some heat of formation or something like that. So this is the simplified view if you have, if you don't have a phase change. If you have a phase change, so let's do a little sketch for that. So here's enthalpy. So we are plotting enthalpy as a function of temperature. And we have some reference value. So for example, this is the heat of formation of our component I. So there's our heat of formation. And this is at our, at some specific temperature T, let's call it TF. Now let's think, so let's say we are starting out in the solid phase, right? So the temperature is low enough, we are in the solid phase. And of course, as we heat up the solid, its enthalpy will rise, even though it's a solid, we can talk about its enthalpy. So it's a solid down here. And then as we heat it up, the enthalpy will rise, and then we'll get to the melting point. So Tm, melting point. And then at the melting temperature, right, this is still on the side of it being a solid. At the melting temperature, it takes more energy just to melt, just to go to the liquid form. So there's a jump here. And now we are in the liquid form, and we are operating in a different gradient. So here we have the heat of melting. So that's the energy that it takes just to melt 1 mole or 1 kilogram. Depends what basis this is written in. But here's our heat of melting. So it costs a certain amount of energy to convert that 1 kilogram to liquid form. And then we will keep rising in our enthalpy until we reach the boiling point. I mean, I know this is all obvious to you now. You've been through thermodynamics, right? So you've reached the boiling temperature. So to the left of this point, you are still in the liquid form. But now you need energy to vaporize yourself into the gas form. So there's the heat of, latent heat of vaporization. This is actually, yeah, there's a proper term, latent heat of melting, I think. And so your latent heat of vaporization, so it costs you energy just to vaporize everything. So HLV for the latent heat of vaporization. So now we boil into the gas, and now our enthalpy keeps rising as we raise the temperature past the boiling temperature. So if you are in the same phase, so for example, if we were here, let's say, so if, for example, we knew the enthalpy at this point, so if that was our reference enthalpy, so we knew an enthalpy here, and then we knew, so this was our reference temperature. And then we said, well, Cp is approximately constant. So if I just multiply by the temperature difference, then we'll get an estimate for the new enthalpy. So we started with this enthalpy, then Cp delta T plus that reference value, that will get us to the new enthalpy. So that's how we would in the same phase, that's how we would estimate the enthalpy at some new temperature. So as long as this temperature is below the phase change temperature, and as long as Tref is in the same phase, it's as easy as this. And it's still easy if you go across phases. You can see you just need to add in the latent heat in each case. Your heat capacities will likely have you'll have different heat capacities in the different phases. That's fine. You just have to look up what it is. And that's it. That's how you can get to enthalpy. So I went through all that just to be able to say, whenever we see enthalpy, we should say, my friend, right? I know how to get you. When we see things like this, we say, I don't like that. I don't know. It's going to be a mission to get this. But enthalpies to us as engineers, oh, that's nice and easy. I know what to do, right? I see there's a plus sign missing. Okay, so that's that balance is looking better to us already. And then still on this side, we don't like this E over here. Let's see. So on this side, everything looks easy now. This is shaft work. So we just look at the motor. We see, oh, it's a 200 watt motor, or whatever it is. And then Q dot, that is basically your whole heat transfer course. So in heat transfer, you learned how to estimate the log mean temperature difference, and you multiply that by UA, the overall heat transfer coefficient, and the area. So that type of calculation is very much behind these Q dots. So that's easy to get. So both these are easy. And now we've got our friend here, enthalpy, and this is nothing but the molar flow rate. So all of this is easy now. The right-hand side is pretty easy. And then on the left-hand side, I think I've done this a bit too quickly. I'm supposed to differentiate something out here. But this E, we also want to improve on. So, so we've got this part, and then this E. So yeah, and okay, so here we are just saying we usually ignore these parts. We did say earlier about elevation. Yeah, this part. So all of that. So enthalpy is like that, and so we wrote it like that. And then if you are working towards a steady state, right? If you want to find the steady rate of conversion or something, then of course this term is a 0. And then you are left with this nice, very easy equation to work with. Okay, so your equation then looks like that. Okay, so this is starting to look like an equation we can work with. This is looking practical. It's we can do calculations with an equation like this. It is for steady state, right? Now, one thing to note is that all this is generally true. If you think about what we started talking about from the beginning, we did not assume anything about the reactor. We didn't talk about any reactor. This was just, there was some space, some fluid flowing across the space, and because we don't have a reaction to worry about here, we are just counting energy. Because we don't have to worry about this, we don't have to worry then about whether it's perfectly mixed or not mixed, or a plug or flow or batch or whatever. So this relationship that we've uncovered here, this is always true. As long as you have flow in, flow out, well, if you don't have, then you get zeros there, right? So this relationship is always true. It applies to all 3 reactor types of ours. So that's good. Now let's see. We still don't see a heat of reaction as yet, and we know that concept exists. So let's see if we start working with a reaction, how that will change. So just to pause there, any questions or comments so far? Okay, so if we have this reaction, and here obviously I'm trying to write it in a general form for some unknown stoichiometric coefficients A, B, C, D, lowercase. So you would obviously substitute your, well, I mean, there's no reason to do this because it's not general anyway. You could have more species, but anyway, it's kind of a good example. So let's keep going with this. So let's say that was our reaction. Then we can just expand in terms of, excuse me, in terms of our species. We can see we have these 4 components. And let's say in addition to those 4 components, A, B, C, D, we also have a component I, an inert, something that's not involved in this reaction. So there are 5 species. And so our total energy due to flow of enthalpy, that's simply the sum of each of those. So we can take the enthalpy of A times the molar flow of A, and we do that, and we get the total enthalpy in, right? Then, of course, we could do the same for the exit. So we could say the enthalpy out and FA out, that's how much energy is leaving as enthalpy, right? So this H is molar enthalpy. So the product is the enthalpy flow. Okay. Now, something to note here, something that's a little bit strange to us is that now our enthalpies have these subscripts in and out. And we don't like that. In a way, that's a little bit offensive to us, right? Enthalpy is this nice pure concept. It's just the energy of a component at a certain temperature, right? When we were drawing this thing here, we weren't talking about was this at the inlet or was this at the exit. So it seems very strange to us now that our enthalpies have subscripts in and out. And the reason for that is just that we are trying to specify a temperature here. So let's see, I don't want to save these little drawings. Let's see, you see I was teaching fundamentals this morning. What's today? This is drawing 1 today, right? So, so in our reactor, we've got an inlet point and an exit point. And we just said we have to evaluate enthalpy at the right temperatures. We also said right at the start that the temperature will change across the reactor because of the reaction in between. So we can identify that there exists a certain temperature here, T in, and a certain temperature out here, which is, let's call it T out. So we've got these 2 temperatures. So the molar enthalpy is calculated based on the temperatures at those points. So that's why we have the subscript out. It doesn't mean that enthalpy inherently changes just because it's at the exit. It's there because the temperature is different there. So we evaluate the enthalpy of component A at the exit temperature, of component B at the exit temperature. And so that's why we have those subscripts. Okay, any questions or comments on that so far? Right, so that's our total enthalpy at the exit and entrance. So that specifies these parts. These parts we aren't so worried about yet. Let's just say we aren't adding shaft work and we aren't adding, or we'll just keep those as symbols, right? So we won't worry about these. We know we can get numbers for those anytime. Right now, we have these 2. And of course, we have also been doing in the sections before what we are doing right now, we had also developed this mole relationship. We said the number of moles of I in the reactor, the amount left over, is equal to what we had initially, so Fi0, and then minus the amount that reacted away. So we said mu I, and then we typically referred it to some component. And we typically wrote this as X FA times FA naught. So that was the mole balance. And then we, of course, also referenced our component I, our inlet component I to FA naught. So we wrote this as capital beta I, and this was FA naught. And so by the end of the day, we could say that our molar flow rate was nothing but FA naught times all this stuff. A naught times all this. Right, so that was something we used quite a lot in the first section. And now we are talking about molar exit flows. So each of these molar flow rates, this is what we are left with exiting the reactor after reaction. So we can replace all these by these expressions, right? By the right-hand side over here. So that's what we do. Yeah, so this is all done in painful detail, yeah. And so our this term, we can write them in that way. See, I don't know whether you want me to do this like so. I can say F in H sub I in so minus the same thing out. Yeah, maybe I'll just do the general form here. So we know we have this. And then this we are going to say equals. And we'll leave all the FI ins here, or let's rather write these as FA in times capital beta sub I, right? So you agree this is the same as FI in. And then for FI out, we'll use this. So we are again referencing it to FA in like this, right? So we've just replaced FI out. We've just replaced this part here by the right-hand side here, right? So we know that mole balance applies. And now we can group out certain things. You can see FA in theta, we can group out like this. Let's see. What is it aligned here? So aligned there. Okay, so so this FA in theta, we're just going to move this across here. So this is HI in, and now I'm getting rid of this part. So I'm going to take this off. So this theta here. So FA in theta. So I'm going to move that part over here. So this is minus H sub I out, right? So that's the only change. I've taken this term and stuck it in here, right? So that's fine. And then if you look at this, does this part look familiar? Maybe this XA is also not an I thing. So it's XA, you take this out here. You can remove this whole thing. It's not indexed with I, so it doesn't have to be in here. So we can take it out there. And then here, you could take this out. So I don't think it helps too much over here. That's fine. Okay, so now if you look at this, what does this look like? What would you call this? Any takers? And this is your high school chemistry I'm asking you about, right? So what's the thing we're looking for all this time? We were worried, where's my heat of reaction, right? Well, I don't know how much more direct I can be, but this thing is nothing but your heat of reaction. Remember when you calculate a heat of reaction for some, so in our reaction here, we've got A plus B gives us C plus D. And we know that the heat of reaction here, delta H R minus, so that's heat of products minus reactants, right? So it's going to be CHI or CHC plus DHD minus AHA minus BHB. So this is the heat of reaction. And if you look at this, that's exactly what we have here. This is heat of reaction just per mole of some general thing reacting. If you wanted per mole of component A, for example, reacting, then you have to divide by that divided by A. Divided by A, which is 1 over there, divided by A. Right, so that is nothing but our heat of reaction. So there it is, our heat of reaction has now appeared. So this is, that's heat of reaction. So now we can say this is equal to the heat of reaction on this side. Delta H R Not sure why that's not working. Let's just copy this one. Okay, so that term is looking better to us. And we know that for given reactions, we can just look things like this up. We also have this stuff here, right? The difference in enthalpy between two temperatures. So this part, we also expect that we can evaluate fairly easily. And so if we go back to that picture we had before, oh no, I think I've saved over it now. But that one with the enthalpy, and we said we start from a reference, then we jump to a new, and so on. So let's do it here. So we said we've got enthalpy in temperature, and so we can go from here to here. Then in the liquid, it's here to here, and then in the gas, it's something else. And so we can evaluate the change in enthalpy by looking at the change in temperature. Now, what we have is a difference in temperature between inlet and exit. So let's say this was an exothermic reaction. So our inlet temperature, T in here and T out there. T out. So let's say it was between here and here. Then all we need to do is get the area under this slightly weird looking shape. So this area is going to be, or the integral under this is going to be our enthalpy difference. So we just need this enthalpy temperature profile for each component, right? So you do have multiple components here. There is a sum over these. So this we can calculate that difference for each component and just add them together using the inlet molar flow ratios, and then that will give us that term. So we know how to work with this also. And especially if the temperature change is not so big, if the temperature change, for example, is in a small range here, then we can just Cp delta T this, right? And, typically in your reactor, you are not looking for big phase changes to be happening across your space. So quite often Cp delta T is good enough for the difference between the inlet and the exit. And so most of the time, this thing is as simple as a Cpi delta T. So theta I is Cpi, and the delta T is, of course, between the, I guess the way it's T in minus T out. So this is T in minus T out, right? So this is for no phase change or anything. Yeah, so now this equation really looks nice and friendly to us. Heat capacities here, temperatures there, inlet molar flow ratio, molar flow rate, heat of reaction, conversion, molar flow rate. So now we have a nice, really easy form of our energy balance. So all that is done in painful detail with those 4 species in that. And there's an example here. Yeah, well, this one is just on the mole, so you can work out the molar flow rates. And then I think a bit later in this, we get heat capacities and heats of formation. So that first example, you can do it and just get molar flow rates, and then you can multiply by heat capacities and heats of formation and see that you get the same heat of reaction. So you can calculate the heat of reaction using the method we just outlined. Okay, any questions or comments there? I haven't been looking in the chat. Let's see, nothing. Okay. All right. So that's what we have. So now we have this very easy equation to work with, where okay, so let's just write it for ourselves here, so we can say this part we've got Q dot plus shaft work. What's that equals 0. So this is an easy form of our energy balance. Right. Now let's think about the addition of heat. So as we said earlier, adding heat to the reactor is typically in this form. So there's some overall heat transfer coefficient, some area, and some temperature difference. And this temperature difference is not between in and out. Of course, if this is heat you are adding due to some external source, then we have to look at the temperature difference between the source and the reactor. And just for convenience, let's use the CSTR as a basis. So here's our CSTR. Here's our stream in, and maybe just to imply it gets hot in there. Here's our stream out at temperature T out. So this is an exothermic reaction. So the temperature goes up just because of the reaction. And then we've got a T in here. And now let's say, so we know that the temperature tends to rise here, that the reaction is exothermic. So this reactor does get hot. So it gets hot in here. So what we will try to do is add a jacket to cool things down for us. So here's a jacket. And we've got flow across this jacket. So you can imagine a jacket as you can imagine this as a double pipe, right? So just in terms of, how you would make such a thing, let's imagine our reactor is like a big tube, right? So, let's say our reactor looks like that. And in cross section on the inside, of course, you've got this kind of thing. So there's our reactor. And then our jacket is going to be basically another tube that goes around this reactor. And we've got a little pipe here. And another little pipe there. So we've got some heat transfer fluid that's also flowing here. So flowing through this jacket, we've got some fluid flowing. And we are saying that this reactor gets pretty hot. So in here, in this reactor, it gets hot. And we are trying to cool things down. So we expect that our jacket, the fluid in the jacket comes in cool, and then by the time it reaches the exit, it's warmed up. And so it's leaving here. So in our reactor, this is a flow reactor. So we have to draw, there's an inlet stream here. So into the space and out of the space. That's our reactor flow. And then things heat up in there. And so in here, we've got T in, and maybe we want to say T in reactor. And coming out, we've got T reactor, right? And I'm just saying T, I'm not saying T out, because remember, if we are regarding this as a CSTR, then it's perfectly mixed. That means your exit temperature is the same as your temperature in the reactor. So I'll just call it TR. And then across your jacket, we are trying to cool things down. So we expect that we will have a lower temperature here. So this is T in for the jacket. And then the jacket temperature will rise because it's absorbing heat from the reactor. And so T out jacket is what we can label here. Right, so you've got jacket in and out, you've got reactor in and out, and so you've got 4 different temperatures. And we do know how to handle a situation like that, right? In heat transfer course, you learned about log mean temperature difference, and then all you need to do is multiply by the overall heat transfer coefficient between the two, and there's the contact area between the two. So the area, that would be the area between the jacket. So this outer wall area here, for example. So what can I use here? So this outer surface here, this would be your heat transfer area between the jacket and the reactor. So your Q dot will be the heat transfer coefficient, the overall heat transfer coefficient, the area between the jacket and the reactor, and then the log mean temperature difference between the reactor and the jacket, right? So that's how you would get a Q dot. What do we say in the notes? So yeah, delta T log mean, there's the formula for the two. And then here we're just pointing out, we're just giving some labels here. So we're actually saying here, the temperature on the reactor side is about the same because the jacket is sitting on the reactor. The jacket is not sitting on the inlet point. So if this is perfectly mixed, then from the reactor side, we are seeing the same temperature at all points between the jacket and the reactor. So instead of saying T in and T out, right, that's not right. Actually, it's the only temperature the jacket sees is T, the reactor temperature. And then, of course, you've got the two temperatures, jacket in and jacket out. Okay. And then if our jacket fluid is fast enough, right? So if you blast through this jacket, excuse me, if your flow rate through the jacket is high enough, then this jacket fluid doesn't stay long enough for its temperature to change that much. It will have to change to some extent because, of course, it's absorbing heat. But if the difference is maybe like 2 degrees or something like that, then we can say this jacket temperature can just be approximated as a TJ. So that will make it easier for us. Yeah, sorry, I just need to hydrate my throat. Just give me a second. Okay, so let's see. So we can simplify things quite a lot like that. If that's the case, let's see, quite a few things have changed here. So this is Q, right? So it's UA times delta T log mean. So delta T log mean involves all that. And then what you can say is, yeah, so if you do a balance then on the jacket side, right, so that's what's happening here. Up to this point, we were just talking about Q. We weren't doing a balance yet. We were just saying how you can calculate the transfer rate, the heat transfer rate. So we weren't as yet doing an energy balance. And now, of course, we are trying to do the energy balance on the reactor. But what we would like to do is simplify our expression for the jacket. So what we are doing now is actually writing a balance on the jacket itself. So you can say there's a certain enthalpy flow into the jacket. There's a certain enthalpy flow out of the jacket. And so we are writing a balance just on the jacket itself over here. So this is the temperature at the inlet point of the jacket and at the exit. So your here's your flow of energy, mCp delta T, jacket in and jacket out. And then between those points, the jacket is exchanging heat with the reactor itself. There's your log mean temperature difference, UA. Right, so if you look at all this, let's see, what, and then if you divide through by m dot Cp, right? Remember, on the jacket, your mass flow rate is not changing. The jacket is not reacting. There's no reaction in the jacket. We don't want a reaction in the jacket. The jacket is just a heat transfer fluid circulating in the jacket. So this is all constant. And so we can divide, so in this equation, you can divide and write UA divided by m dot Cpj. And then you can take the exponential on both sides to get rid of this log. So if you do that, then you'll get an expression like this, okay? And And then you can, so we got this now from our jacket balance, right? This was a balance on the jacket. So we got that relationship from the jacket. What we actually need is the Q dot. And so Q dot, if you look on the jacket side, if you substitute this for TA2 into that jacket balance, then you get that expression. And then, like we said, if your mass flow rate in the jacket is high enough, then this term goes approximately to 0, right? So you are taking the exponential of a very small number. And the exponential of a small number, if you think about your exponential function, it looks like this. So remember, it goes through the 1 there. So it goes from low values and then exponentially explodes. So that's your exponential function. But if you take very small numbers, then the gradient here is approximately 1. So down here, you can, the exponential function, you can approximate it. You can say for small values of x, this is approximately equal to 1 plus x. Right, you can maybe take out your calculator and try it out. So try out the exponential function for x equals, for example, 0.01 or 0.05, and you should get 1.01 and 1.05 approximately. So the exponential function can be approximated in this way for small values of x. So if we replace this, then this is going to be 1 plus this thing, right? And then the ones can cancel, leaving us just with this part, right? So the ones cancel, the ones go away. And then you can see the this m dot cpj can cancel with this m dot cpj, and it leaves us with this really simple form here. So if your flow rate on the jacket side is quite high, and if it's a CSTR, then your Q dot is as simple as this. So all we need is the overall heat transfer coefficient and the area of contact between the jacket and the reactor. We need to know the average temperature of the jacket heat transfer fluid, and we need the temperature in the reactor. And the temperature in the reactor, of course, is part of our balance here. So we can stick all that in for Q dot, and that gives us a nice easy form like this, right? And then, of course, W dot S, that's simply the shaft work. So we just look at the motor that's driving the impeller, and we just add that number, the power rating on the motor. That's the work done. And then we get this really nice equation. So this tells us that if we achieve a conversion of X in the reactor, then our temperature must be this value, this T. Or if we go and stick a thermometer in or if we measure the temperature in the reactor, the value of the temperature there can be used to estimate the conversion in that reactor. Okay, any questions or comments so far? Okay, so all this is for the CSTR. And there's just a comment here that this heat of reaction, this is a function of temperature generally, but we can expand this. So the heat of reaction, we can write it in terms of some reference temperature. So you can work out the heat of reaction at some specific temperature, and then you can work out the heat of reaction heat capacity. So this delta here has the special meaning. It's, did I write it somewhere? So that delta CP means specifically this delta CP equals mu I over mu A times CPI. So you take each of your species, multiply their stoichiometric coefficient from the reaction by that heat capacity, divide by the stoichiometric coefficient of A, and that will give you the overall heat capacity change due to reaction. So that's, if you like, the CP version of the heat of reaction. So this is a convenient form to expand your heat of reaction to. So you can say, well, as long as I work out my delta CP for that reaction, then I can expand this for temperature and I can get that. And the reason we like to do that is we often say, well, delta CP is often a very small number, right? This whole term is often quite small. And so an approximation to make is to just use the standard heat of reaction. So again, we've made it nice and easy for ourselves. We just go and look up the standard heat of reaction. And then that's just a fixed number we can stick there. And then we've got this kind of heat exchange calculation that's easy. And this also is simply the heat, the temperature difference across the reactor. So this is quite a practical form. You might feel we've made too many approximations in here, but actually this does give fairly good results in practice. So all those approximations do work fairly well. And even though this equation looks ridiculously easy to work with, when used in practice, it does give good results. So that's a nice form that we have available now. Okay, any questions or comments there? Right, so all this applies to our CSTR. And yeah, you can follow this example. In this example, you actually probe those assumptions. So you are given enough information here to solve the equation without all the approximations. So you can calculate jacket temperatures and all of that. And so do work this out and check all those approximations. It's plotted here. This is the final answer when you do all that. And you find that they are close enough. So it's around about a 3% difference, right? Your a value of 0.03 for your conversion difference. So that's pretty close. So that just shows how close, how well that equation works. This is, yeah, what was this? Yeah, if you increase your jacket flow rate, then one of those gets even closer and it's even better. Okay, so that's all on the CSTR side. For the tubular reactor, you can read this, and but it's more of the same. So the same expression does apply, but now we are in a plug flow reactor. You regard this expression now as a thing that applies for all points along that reactor. So this equation now is about x, which is varying in z, right? If z is your distance along the axis of this PFR, then that x is changing as we go down that PFR. So x is changing, so that means t will also change. So you will effectively use this equation to, for example, recalculate the temperature as you progress along this tube. And you do that because in your material balance, right? Remember, this is only the energy balance. We still have to solve the material balance to get the conversion. So when we integrate our way along here, let's see, you should have it here, right? So as we integrate our way down the tube, right, this equation still applies. I know we had this in the isothermal case, but that was just isothermal because we thought RA was constant. Now RA does need to be recalculated as we go down the tube. So because temperature is changing down the tube, when we calculate RA, so remember RA, we established in the beginning is the kinetic rate constant, which is Arrheniously related to the temperature. And then, for example, if it's a first order reaction, it looks like that. And then that typically we write like that. We write it in terms of the conversion. So RA, so if we take this equation, this one, then we are trying to do this, right? Okay, I'm just going to write it. df d equals RA. So we have this. And here we have XA, and this is this if right. So this ODE, you can see the variable is XA, and there's your XA over there. But and this volume we can write in terms of Z and A. So the area, so A dZ is dV. So and I just want to write that A over here. This is the area, right? Not component A. This is maybe just add a C to emphasize that's area. So that's the equation we are solving. And now this is a function of temperature. And so we didn't know how to handle this case before, right? We knew that if temperature were changing, then we couldn't use the equation anymore. But now what we have is this expression. And what we can do with this is rewrite it. We can say T now, we can translate this as temperature is a function of conversion, right? If you look at this equation, you can see there's conversion there and there's temperature, right? For the CSTR, T out equals T, okay? So there's our T. We do have T-ins and other constants here. So those are constants. So by the end of the day, what we can say is we now have an energy balance that we can use to establish the relationship between temperature and conversion. So we've got T of X now. So now we can write this as T of X. So this whole equation now becomes solvable. So that's the big step forward for today. Now the temperature is varying, but through the energy balance, we have a relationship with the conversion. So we can get rid of this temperature variable, and we have now updated our mass balance. It is a more complicated relationship between X left-hand side and right-hand side, but still it's one differential equation and we can solve this. Right, so that's what we're trying to do here. The same thing applies. This was in the case of the PFR, right? In the case of the CSTR, we have FA naught X equals RAV. And again, this RA had a hidden temperature relationship. So this was our K of T times CA, and that CA we can rewrite as CA naught 1 minus X. So that's there. But now because we have this energy balance, this T is a function of X. So now we can even handle the case where the temperature is changing. We still have one equation in terms of X. And if we are, for example, given X, we can calculate V like we did in our Levenspiel plot. Or if we are given V, we can calculate X, or so whichever way you want to do it, or what the design question is. You can see that you can actually use this to construct your Levenspiel plot. Let's think, well, that's in R, yeah. So I mean, R being, with the temperature being a function of X, right, regarding all this as R. Now our R will have a different relationship with X because of the temperature influence, but we have a formula now for that, and so you can create the Levenspiel plot even for the case where temperature is changing. Okay, any questions or comments there? So that's basically it for today. This is the last few things we said here. That's critical to follow what we are doing, right? This is what we are trying to do. We know temperature is changing in these reactors, but the energy balance lets us relate it to the conversion. And so now we can link back to the theory that we are familiar with, right? So that's the message for today. And then in the tutorial questions, you can go ahead and use that now to solve those other problems that it wasn't clear how to solve those problems without the energy balance. Okay, any questions or comments there? Okay, it seems not. So we'll stop there for today. See you next time.